So good evening friends, we start magnetic flux linkage testing. Method which induced magnetic flux within a ferromagnetic specimen. So without ferromagnetic it cannot work. Then 6 localized magnetic flux linkage fields along the surface. The 4 steps in MFL: magnetize the test object in the direction such that the lines of magnetic flux are distributed by discontinuities. Maximum to perpendicular. Which type of probe? It depends on that. Scan the surface of test object with a magnetic flux sensitive detector and magnetic flux sensitive detectors. Then process the data to accentuate discontinuity signals. Present the test result clearly for interpretation. The method is based on principle that magnetic flux is locally distorted by the presence of a discontinuity. The localized distortion causes some of the magnetic fields to exit and then re-enter the test object at the surface and near subsurface discontinuities. Magnetic dipole caused by field distortion is called magnetic flux linkage field. There are limits to deep discontinuity sensitivity using method. However, these limits are controllable to some extent by the intensity of induced magnetic field, by features of the discontinuity such as depth, size, shape, by relative orientation of discontinuity, magnetic flux lines, slot or keyways in the reverse side of the magnetic bar, and internal midwall discontinuity in magnetized test object. Detection of flux linkage field. Unlike the particles used in closely related magnetic particle testing method, MFL employs Hall effect sensor to detect flux linkage field. The core of a Hall effect sensor is semiconductor crystal, which has a constant current applied to it. The Hall sensor is a 4-terminal solid-state device which produces an output voltage proportional to their input current, magnetic flux density, and the cosine of the angle between the flux lines and the face of the semiconductor crystal. For example, a 10-degree off-angle orientation results in 1.5% decrease in measured the flux density. The magnetic flux lines passing the Hall probe induce an electrical voltage potential. The polarity of the voltage potential changes with direction of the magnetic flux, with one side of the sensor crystal becoming the negative portion and the other side positive. So these Hall probes may be configured oriented parallel or perpendicular, transverse probe, or axial probe. It depends what to find out. Microwave testing, MW, and millimeter wave NDT are most often applied to electrically insulated dielectric materials such as rubber, many composites, ceramics. However, they may also be applied to conductive materials. These techniques are useful for measuring the controlling the distance from the geometry of a specimen involving microwave imaging or holography, evaluation of spectroscopic analysis of microstructure content of chemistry, detection and sizing of discontinuities in metal. Microwave measurement setup may contact or non-contact and divided into three categories: reflection, transmission, and scattering. Reflection measurement generally use one antenna for transmitting and receiving signal. Transmission measurement place an antenna on each side of the specimen, and scattering measurements are obtained using several transmitters or several receivers positioned at key position. So change in dielectric constant. The interrogating microwave energy is emitted from the transducer, and signal of interest may be caused by localized change in the dielectric constant of the sample, including delamination, surface breaking, discontinuities, moisture content, and impurities by the polarization of signal due to discontinuity or sample material orientation effect. Test frequencies are between 300 MHz to 300 GHz. So wavelength range from 1 meter down to 1 mm. Microwave in the frequency range below 40 GHz are generally referred to as a millimeter wave because that is the length of scale of their wavelength in free space. However, these interrogating waves can penetrate dielectric test object. The depth of penetration governed by material's ability to absorb microwave energy. Ground penetrating radar, GPR. GPR system typically include a radar pulse generator, transmitter, receiver, antenna, and equipment of electronic data acquisition storage. The electromagnetic radar pulse propagates into the specimen, and wave reflection occurs at localized changes in dielectric properties. The frequency generally varies between 500 MHz to 2 GHz. Higher frequencies allow shallow interrogation at high resolution. However, resolution must be sacrificed when penetrating ability of slower test frequencies is required. Position enhancer for data. Position encoder for data. Data collection is usually triggered by position encoder, such as a survey wheel. The encoder triggers data acquisition at regular intervals. Individual waveform collected along the path of the radar antenna can be viewed collectively in a B-scan data presentation. Depending on the application, system are described either ground coupled or air coupled. Air coupled or launch system use antenna position at the above at a height related to the central test frequency, whereas most ground coupled antennas are positioned with the housing directly in contact with the ground. Air coupled systems offer higher inspection speed, but ground coupled offers greater depth of penetration at a given test frequency. Okay, we'll stop here.